So welcome. Hopefully the quiz went well. Let's work on the quiz right now. Okay, so here's the quiz. It says, consider the sequence, 4, 2, 1, a half, a fourth, an eighth, etc. And part A is write an as an explicit function of n. So in particular, what do you notice? What do you notice about this sequence in terms of what it's doing or what it looks like?
Multiplying by a half each time.
Yep, it's multiplying by a half each time. And if you remember, when you have multiplying by a half each time, what you can do is you can write the first term. So let's write this out. The first term is 4. And notice that we're multiplying by a half. So what that says is a sub n is equal to 4 times 1 over 2 to the n. And that was part A. Any questions on part A? Any questions on that? Okay, so now we want to write down an as a recursive function. So remember, recursive functions mean you have to write a sub n in terms of the previous one or ones. So in this case, again, it's multiplying by a half each time. So what we can do.
Is a sub 0 the 4, or would it be?
Yep.
Okay.
Yep, a sub 0 is the 4. So I'm going to write a sub n is equal to a half times a sub n minus 1. And as you mentioned, you also have to write down the first term. And that's when it is recursive in just the prior term. If it's recursive in 2 terms, you got to write the first 2 terms. But in this case, it's just single recursive. So a sub 0 is just the first term, and that's 4. Any questions at all on part B? Any questions? Okay, nothing magical about it, but you have to be able to do this. Okay, part C. The question is a sub n bounded? What does bounded mean?
There's restrictions like as to what the number goes to.
Yeah, in particular, the absolute value of a sub n has to be less than a value, a fixed value for all n. And so in this case, is it bounded?
Yeah, I'd say it's less than 4 because it's just getting smaller as it approaches 0.
Yeah, and notice that a sub n is never negative. So there's no issue with the bottom side. The bottom side is clearly bounded. Yes, it is bounded. Since absolute value, I think I'll do it this way. The absolute value of a sub n is less than 5 in particular. Okay, you can say 4.1 if you want for all n. Any questions on that? Okay, let's do part D. Part D is a sub n monotonic? So what does the word monotonic mean?
Isn't it like its domain doesn't ever really like change, or it becomes increasing, like it always stays increasing or decreasing? So if the domain is always increasing, it's monotonic. If it's always decreasing, it's monotonic, right? Or
really close, except the range, not the domain.
the range, yeah, sorry.
Yeah. The domain always goes up because you go 0, 1, 2, 3, 4, 5. It's the range that needs to be decreasing. And in this case, if you look at the numbers, they go down, right? So I'm going to prove it. I didn't expect you to necessarily prove it, but let me show you how to prove it. So the answer is consider f of x equal, how about 4 over 2 to the 2 to the x, which, by the way, is equal to 4 times 2 to the negative x, which is equal to 4 times, and 2 to a power is the same as e to the, so let's write this out, times e to the, and then it's going to be negative x ln 2. Figure I might as well do this, might as well do some calculus. I didn't expect you to have to do it, but let's do it formally. Well, how do you show a function is decreasing?
Derivative.
Yep, take the derivative. Then f prime of x is equal to, well, it's going to be negative 8 ln 2 times e to the negative x ln 2. But that's certainly less than 0, because e to anything is positive, and negative 8 ln 2 is a negative number. So therefore, it is decreasing. Okay, I'm not going to take out points if you didn't prove it, but I might as well show you the proof because you should do something. So therefore, actually, therefore it is monotonic because that's our word. Sometimes we'll say monotonically decreasing. E. Does the sequence AN converge or diverge? Explain your reasoning. So what can you say?
Converges.
Yeah, how come?
It goes to 0.
Yeah, if you make, like, say, a limit, for example, of like the function of a of n, and you put it would approach 0, it'd be like 4 times 1 over. I mean,
all right, let's do it the way we talked about it 2 days ago.
there's like a theorem if it's monotonic.
Yeah. Since it is bounded and monotonic, it converges by the theorem. On bounded monotonic sequences. And that's it. Okay, so C and D, we're supposed to set you up for part E. Is that clear? One of the things we're going to do in this class, and you got to get used to it, is we're going to do a lot of proofs. So in the proofs, you need to state the theorem you're using when you're proving something. And here we're using the bounded monotonic sequence theorem. Any questions on that? Any questions? Okay, so that's the quiz, and that's it. And again, it's pretty standard. It's, you know, a lot of the things that we did a couple days ago, but it's very different. Hopefully you all agree it's very different than what we had been doing for the first 6 weeks of class. We're really, it's like a new, doesn't it feel like a new class when you look at the stuff we're doing now?
Yeah.
Yeah, that's how it's going to be. And today have nothing to do with the first 6 weeks of class also, but it has a lot to do with 2 days ago. So we're really in a new spot. Any questions at all about anything? Okay, if there's no questions, let's go on and talk about the main thing we're doing today, and that is we're going to be looking at series. And to get there, we got to first talk about a sequence of partial sums. I think I'll do it by example before I get into the formal definition. Let's look at an example. Okay, well, we could look at the example that we just looked at, and that was we could look at AN was equal to 4 times 1/2 to the n. Okay, we can look at that. And by the way, sometimes it's good to look at it as 4, 2, 1, 1/2, 4th, an 8th, dot, dot, dot. Okay, so I'm just going to use the example from the quiz since we were just looking at it, and it should be fresh in our heads. And what we want to do now is I'm going to create a different sequence. So I'm going to start with the sequence AN, and from that sequence, I am going to come up with a new sequence. And instead of A, I'm going to use S, as we'll see in a little bit why we're going to use S. So consider the sequence as follows. Maybe I'll say sequence S as follows. So first thing, S, I'll look lowercase s. S1, I'm going to actually go S0. I'm going to go a little differently in the book because this is going to help us later. I'm always going to start at the 0th element. S0 is just going to be 4. So it's just the first term. S1 is equal to 4 plus 2. Okay, I know you could all do that in your head and say it's 6, but I want to leave it as 4 plus 2 because that's what we want to look at. S sub 2 is equal to, any guess on what it might be? Any thoughts? Yeah, but let me write it as 4 plus 2 plus 1. So what these things are is these are called partial sums. What we're going to be looking at is we're going to take a sum of that number term. So S3, I'll do one more. I'm not going to do them all because I'll be here all day doing it. S sub 3 is equal to 4 plus 2 plus 1 plus 1/2. Any questions on that? Okay, now I could do it in general for this one and do the following. And that is S sub n, because I want to define a sequence. Instead of just saying, well, I'm looking at a pattern, I kind of understand the pattern. Now let's see how you really define it. And the idea here is when you're adding a bunch of things, what symbol do you use to add a whole lot of things? We used it a lot last quarter, actually.
Summation.
Yeah, so we're going to use a summation. And the good news is this tool does have summation in there. N equals 0. To, sorry, not n equals 0. k equals 0 to n of a sub n. Okay, so in particular, by the way, ours, I might as well finish it off. Is going to be the summation k equals 0 to n, and our a sub n was 4 times a half to the n. Any questions on that? Any questions? Okay, so now let's define it. Now that I've kind of done it by example, now let's have the formal definition, which is kind of up there already. So this is the definition. And that is, let a sub n be a sequence then the sequence of partial sums is defined by what we just wrote. Let's make it a little bigger. Actually, see if it'll let me. Good. And this is the sequence of partial sums. Any questions on this definition?
So I have a question.
Yeah.
So you know how you gave the example, the quiz example that we just did, the 4 times 1/2 to the n. I don't really understand the partial sums. Like,
okay, there's one error. Sorry, I'm fixing it now. My guess that may not be what the issue was, but it's a k, not an n, that we're adding. Was that the issue or not?
no, I just don't
Okay.
understand the whole, like, how do we go from 4 to 6 and then from 6 to 7, so on and so forth.
You mean how do you arrive at the answer?
Yeah.
Or what's the definition?
Yeah, how do we arrive at the answer?
Ah, that's actually a very difficult question. And the answer is, we're going to spend the rest of today doing a few examples. Most examples you can't do.
Okay.
Okay. Right now, if you look at, right, and I didn't ask you for that on the quiz, did I?
No.
No, and I wouldn't. But on the next quiz, I will. But we need to get there. Does that sound fair?
Mm-hmm.
Yeah, so that's what today's all about, is how do you arrive at the answer? Actually, two things. One, the first thing, there's a question that becomes before how do you arrive at the answer? And that is there an answer? And then how do you arrive at the answer? Does that make sense?
Yeah.
So, and we'll see what we mean. In this example, there is an answer. But let me do the second definition, because first thing, an answer to what? And that's what the second definition is going to be. I'll put it under the same definition marker, though. The series associated with the sequence AN is defined by the limit as n approaches infinity of the sequence of partial sums. It is denoted by very similar, so I'm going to copy and paste because it's that similar. except instead of an n, we're not going to even put anything because s is always going to mean that, but we're going to put an infinity. Which is that one maybe? No. That one. So, and sometimes we'll use an n equals 0 to infinity. In fact, usually you do, just because n is n stands for number. People like that letter. Doesn't matter whether you use k or n. It's a dummy variable. Just like taking an integral, doesn't matter whether you have a dx or dq, as long as you use the same letter and everything. Okay. So let me focus on series, because that's what we're going to be spending the rest of the entire quarter on, is series. Any questions on that so far? So a series is a number. And that's a really good question. The answer is sometimes. Don't you hate that? So let me give you the next definition. Okay, so it's a perfect question because that's what I'm about to talk about. Okay. The series is said to converge if the limit exists and gives you a number. Otherwise, we say that the series diverges. The good thing is we've used these words in very similar meaning when we talked about integration, when we talked about improper integrals. You talked about it with Bruce when you talked about limits, converge and diverge. So the words, it's not like we've changed what the words mean. We're just changing what we're thinking about in terms of what the words are talking about. And here they're talking about series instead of just general limits or integrals. Okay, but we still are going to say converge or diverge. Any questions on that? Okay, so let me mention a few things in terms of kind of real world practices. Typically, the first thing you do is you say, does the series converge or diverge? Okay, and if it diverges, you give up because it doesn't help to look for the number if there isn't a number. Is that clear to everyone? If it converges, and if it's a well-behaved series, then you go and compute it. If it's not a well-behaved series, you use a computer. The problem with using a computer without doing the first step is the computer will give you an answer whether there is one or not, because computers don't understand what infinity means. Is that clear? So if you just say, oh, go to the first 500 terms, good enough, it may not be good enough because it might diverge and then you're not even close. Does that make sense? Okay, so typically the first thing you need to do is just say, does it converge or diverge? And sometimes that's all you need to understand mathematically. Other times you actually need to come up with the answer if it converges. And if it diverges, it diverges. It's over. Any questions on that? How that works? Okay, so now what I'm going to do, I'm going to do an example. And I'm going to first write the example, and then I'm going to talk about what kind of example it is. I want to do an example that looks pretty nasty, and that's important. It's important to understand that not everything is easy. Let's look at the series. I think I can do that. Good. I think I don't want it to be so big, though. Yeah. That's better. So let's look at the series. the summation, k, let's go n equals 0 to infinity of the fraction qn minus 1 over n to the fourth plus 2n cubed plus n squared. I think we need to make that a little bigger, actually. That's a good amount. Okay. So what's the first thing you should be thinking about?
When n equals 0.
Take a look at, oh, you know what? Let's make that n equals, that's a good point. Let's make it 1. Yeah, you got a problem at 0, so let's not even start at 0. I don't want to go there. We're really dealing with limits, which means that we're only caring about the higher numbers. So I'm just going to start at 1. So now you don't have to worry about the 0 anymore. So what's the first thing you should think about?
Where is this going to go when we plug in infinity?
You could do that. And if you look at that, if you plug in infinity, by the way, you could use L'Hopital's rule. And you get 2 over what, 4n cubed plus 6n squared plus 2n. That goes to 0. Is that clear?
Yep.
Okay. So here's the news. That doesn't tell us anything. It's a good try. Okay, so you got to be really careful about saying it looks like it's decreasing. Okay. It turns out it's not. Okay, this is actually this is increasing for all n. Okay, or for all SNs. Because remember, this is a summation. It's not a sequence of a bunch of numbers like you're thinking. It's a sequence of sums. And each time you're adding on another number. Does that make sense? And that number you're adding is positive. Okay, if n is 1 or higher, you get hopefully it's obvious that's positive, right? The numerator is at least as big as 1, and the denominator is at least as big as 4. Okay, so definitely positive. So it's not decreasing, this is increasing. If you tag on an extra positive thing and you keep adding and adding and adding, consuming more and more, you just get bigger and bigger and bigger. Is that clear? So this is increasing and not decreasing. That's one issue. Okay, so there's all kinds of weird issues on this. What we don't even know is if it's bounded. That's the bigger issue. Does this increase off to infinity or does it not when you're adding? So don't get confused between the sequence of ANs and the sequence of SNs. They're very different. Is that clear? All right, so here's something you may not even want to hear, but I'm going to tell you anyway, because my guess is no one's thinking about it, is you need to think about last quarter, okay? There's not a whole lot we're going to use from last quarter. There's actually 2 things. And what if instead of a summation, what if this were an integral sign? And instead of n's, you had x's? What would you do on this? Again, it's been a while. Been some months. What would you do if you had to integrate this? And don't tell me cry. Okay, or computer, no computer allowed other than typing. What would you do if you had to integrate this function from even 1 to infinity? What would your first step be?
Algebra.
Huh?
Clean it up if I could.
What's
Just
clean it
move.
up mean here?
Perhaps rewrite it. like 2n minus 1 times n to the -4 and so on.
No, you can't split denominators, remember?
Well, I would keep it grouped together in one parenthesis.
Yeah. Yeah, that's not what you do. Maybe
Okay.
I'll say partial fractions. There we go. Finally got someone saying it. Yeah, we use partial fractions. And that's what we're gonna do on this also. So let's use partial fractions. So I am now gonna write down, let's make it a new page so you can see it. I'm gonna write down A. Actually, let's make it a fraction. That's going to be A over n squared. Remember that? Okay, and it's actually A n plus B. I know you're used to having x's, but it doesn't matter whether it's x or n. So again, if you factor this, you get an n squared, and then you'll get an n squared plus 2n plus 1, which is n plus 1 squared. So plus fraction, C, that B should probably be capital B, over n plus 1 squared. And that's actually a Cn plus D. Do you remember doing this? All right, so I am going to assume, which is probably not the best assumption, but we're gonna go for it anyway, that you know how to do this. And if you do this, or maybe we'll do it because it's not so bad. So then we go An plus B. Times n plus 1 squared. Plus Cn plus D. Times n squared equals 2n minus 1. Any questions on that? Okay, if n is 0, what does that tell you? Be careful. Okay, if n is 0, let's look at the right-hand side first, because I think you're not paying attention. 2n minus 1 is 2 times 0 minus 1, which is -1.
B plus D equals -1.
Now remember that we're multiplying by n squared over here. That goes away. So it's just b equals -1. Is that clear?
Yeah.
Okay, so that's if n equals 0. If n is way too big, I'm gonna run out of space. If n is equal to -1, right? You always want, I don't know if you remember, but in calculus, you always want to throw the easy stuff in so you don't have to work as hard. If n is -1, then notice that the first piece goes away, right? The second is -c plus d. Is equal to And I think I'm going to just say, and you understand how this all works, and I'm going to give you the punchline. Sound good? Y'all good with that? So after doing the algebra, you actually end up getting that D is equal to 1, and A and C is equal to 0. And you can convince yourself that works. Any questions on that? Any questions? Okay, so once we have that, now let me rewrite this. And I think I'm just going to copy this. So at least the first part's exactly the same. And the way I can rewrite this now, if B is -1 and D is 1, that means we have -1 over n squared plus 1 over n plus 1 squared. Any questions on that? Let me double check I got that one right. Yeah. Any questions? Okay. I think I have this backwards actually. It's 1 over n squared, and then it's going to be a plus -1. That's the way this works. Any questions on that so far? All right, now comes the interesting part. For this particular example, what I'm going to do is I'm actually going to work this out. So I'm going to write down what this means. And what this means is the following. What it means is we're going to have a 1 over 1 squared. And actually, before I do that, let's put in parentheses. 1 over 1 squared. Minus 1 over 2 squared. And then we're going to add the next one, which is 1 over 2 squared. And I'm just going to copy and paste this guy because then I can just change a few things. One over 2 squared minus 1 over 3 squared. There we go. And then I can keep going. And I can say plus 1 over 3 squared minus 1 over 4 squared. Plus, and I go dot, dot, dot. What? And now take a look at what's happening here. If you rearrange the parentheses, what do you get? Anyone see what's going on if you rearrange the parentheses? Use the associative property. Okay, I don't see y'all jumping in, so
You get a sequence.
yeah, but it's a very special one. So let's rewrite this with the parentheses different. Oops. So we can have 1 over 1 squared, and then we're going to have a plus a negative 1 over 2 squared plus 1 over 2 squared. Just takes a while to type it. Then we can say plus a negative 1 over 3 squared plus 1 over 3 squared. And then you're going to have a plus. And then you have a negative 1 over 4 squared plus 1 over 4 squared.
So 1.
Yeah.
That's interesting.
Isn't this beautiful? That's just 1. It's a beautiful, beautiful series. Okay. Very tricky, isn't it? So in particular, this is called a telescoping series. So how many of you guys have played with a telescope before?
I have.
What happens when you put it away? Right?
It gets dusty.
Well, but you squeeze it up, right?
Yeah.
Isn't that what we do? It might get dusty too.
Yeah. Yeah, you close it up.
Squeeze
Yeah,
it up.
definitely.
And all you see is the lens in the front and the lens at the end, right? So that's why they call this a telescoping series, because what happens is if we give a series like this, you get your first term and you get your last term, but the last term here just goes to 0 because it's 1 over infinity. You see that? So this is a telescoping series, and whenever you have a telescoping series, and you can see it by saying that there's an n and an n plus 1 and you're subtracting. Do you see that? So what we can say in general, see if that works. No. Let's do this. Is that the summation n equals 1 to infinity of a sub n minus, let's go n minus a sub n plus 1 is equal to the following. Well, it's going to be equal to a1 minus a infinity, which is the limit as n goes to infinity of a sub n. I'm just going to write it. It's easier to type. Any questions on telescoping series in this example? Okay, and that's again, because if you sit there and you do the subtractions, all the middle terms go away and all you're left with is the left and the right term, and that's it. Is that clear? Okay, so that's a telescoping series, and they're nice because you can actually come up with the answer. And what we're doing today, by the way, we're going to see if we can come up with answers. Okay, so in our list of things to do, by the way, We just did the telescoping series. Now it's time to do the geometric series. And I'm actually gonna, I think someone even asked about that, is what do you do when you have to add them all up? And this is what we do. So this is for geometric series. So I'm gonna write this without summation sign, because for the proof, it's a little easier to see. So let's do that. So first thing for geometric series, if you remember the formula for geometric series is A naught. So let me just write this down. We're gonna have a summation. First we'll write summation and then we'll get rid of the summation. Oops. Let's do it that way, good. So we have a summation. I like to go n equals 0. The book goes 1, but I like to go 0. Of fraction of A naught R to the n. That's a geometric series. You all agree? In fact, it's what you had for the quiz problem. This is equal to, and what I'm going to do is I'm going to do a little algebra, baby algebra, I promise. I'm going to take that A naught and then pull it outside the sum. It's a constant in every term. And that always works as long as A naught's not 0. If A naught's 0, the whole sequence is just 0, 0, 0, 0, and it's dumb. And then R doesn't even make any sense. So this is always works. So if I can find just a summation of R to the n, then I just multiply by A naught. Everyone okay with that? And that gives me my geometric series. So now I'm going to write down the summation of R to the n without using sigma notation. I can use dot, dot, dot notation because it turns out it's a little easier. Now it's going to be 1. Just leave some space. 1 plus R squared plus R cubed, and I guess instead of leaving space, I'm going to write S is equal to that. Plus R to the 4th, pretty soon you'll get tired real fast, plus R to the 5th, plus dot, dot, dot. Any questions on that? Now what I'm going to do, just for fun, I'm going to take S and I'm going to multiply by R. When you multiply by R, what you get, I'm going to do this on purpose, I'm going to line it up weird. What you get is R plus R squared plus R cubed plus R to the 4th plus R to the 5th, etc. That's what happens when you multiply S by R. Everyone good with that? Now I'm going to subtract S minus RS. What do you get when you take S minus RS? The hint is very easy.
R?
Not quite. 1. Right? Everything cancels except the 1. Do you see that?
Oh, I get it. I'm sorry.
Yeah. Everything cancels except the 1. The R's cancel because there's an R on both of them. But there's no 1 on the RS. So what we can do is factor out the S. So we get S times 1 minus R equals 1. Y'all good with that? And then we can solve for S. S is equal to the fraction 1 over 1 minus R. So in general, the sum of the geometric sequence, geometric series, sorry, is, so remember at the very beginning, I pulled out the A naught. Now I got to put it back in. So it's going to be equal to the fraction A naught over 1 minus R. It's important enough, I think I want to make it bigger. Okay, you need to memorize this. I know the proof is beautiful, but you need to memorize it. It comes up a lot in this class. So not that hard. The beautiful formula. That's better. Any questions at all on this? Okay, so let's see if we can do our quiz problem. Remember, we had 4, 2, a half. I think it's still up there. Copy paste it. So there was our AN, right? What's S? And the hint is it's very easy.
I would say A sub n.
All right, the idea is, yeah, use the formula. You definitely want to use the equation. Okay, you certainly don't want to do the subgroup one at a time. A naught is just 4. 1 minus R is a half. And you can work that out. 1 minus a half is a half. 4 divided by half is 8. Any questions at all on this example?
So I have a question. Is it a coincidence that it's 8?
I'm not sure it might be coincidence. Coincidence. Do you see another 8?
Well, the reason why I ask because it's 4 times 1/2 to the power of n. And if you were to just, if you wanted to, actually, I don't really know where I'm going with this.
You're saying, well, what's 4 divided by half or something like that? Is that what you're saying? Maybe.
Yeah, kind of like a reciprocal sort of thing, but
Yeah, but it turns out no, that's a coincidence.
it is just a coincidence.
Yeah, maybe I'll do another one and you'll see, or I'll let you try it. All of you, not just you, but all of you. So let's suppose AN, let's throw some other numbers in. How about 5 times a third? Oops. A third to the n. Okay, the hint is you don't get 15. But what do you get? If you guys can do it. So find, I guess I should state this question. Find S. And let's see, you can all do it. It's just basic arithmetic. That's the nice thing. This isn't that hard. I think you'll all agree.
15 halves.
Okay, right. So notice it doesn't just go nicely anymore, because that's going to be 5 divided by 1 minus a third. And that's 5 divided by 2/3, which is 15 halves. I forgot the equal sign. So I think your answer is yes, coincidence. Okay, any questions at all on this example? On any of these examples? Okay, now let's go backwards. Backwards is actually, I know this sounds weird, but for this class, this course, backwards is more important than forwards. Okay, right? Let me write it out. x cubed over 2 plus x to the fourth as, shoot. As a geometric series. Okay, actually, I'm just going to, as a series. Stop it there, and let's make it bigger so you can see it a little better. Okay, so does this have the right form? Right? Does this look like an a over 1 minus something to the 1 minus something? Okay, it doesn't, which means we need to make it the right form. Any questions on that? So what we need to do, what the problem is, two problems. One is the plus sign, and the other is the 2. So now we got to go back to, and I've said this is my second time saying this today, last quarter. Do you remember when it kind of looked like it, but it didn't quite have the right form, and you had an extra number there at 2 last quarter? And you wanted to make that 2 a 1? Do you remember what you had to do? It wasn't that hard. The hint is this was in like arc trig substitution stuff.
You like took it out as a constant, so in this case you would like pull out a 2 and it'd be 1 plus x to the fourth over 2, and then you can pull out a constant.
Exactly, exactly. So we can write this, that's perfect. So we're going to rewrite this as 1/2. So it's a bit tricky, but because we did it last quarter, I mean something very similar. And then we're going to have another fraction. We're going to have x cubed. And then we'll have a 1. We don't want that to be a plus. We need it to be a minus, don't we? Can I make it a minus?
If you make the coefficient,
if we make the term negative, that's
Yeah.
probably what you're thinking, right? So that's going to be x to the fourth. Sorry, negative x to the fourth over 2. Let's make that a bit bigger. Any questions at all so far? All right, well now we're ready because now it's in the form of the geometric series. So now that it's in the form of the geometric series, I can use the equation. So I can write that as 1 over 2 times the summation from n equals 0 to infinity and now we look to see what we have. Well, x cubed is our a naught. So x cubed times parenthesis negative x to the fourth over 2 to the n power. Any questions on that? Okay, I want to pretty this up a little bit because you're going to be doing a lot of that later on in the next chapter. So I want to make sure you know how to pretty it up. So first thing, I'm going to get rid of that half, and you'll see why I can do that. If you have a negative to the n, that's the same thing as a -1 to the n. Any questions on that? And now let's look at the power of x. Well, we have x to the 4 to the n, which is x to the 4n, but then we have another 3, so that's going to be x to the 4n plus 3. And then we have a 1 over 2 to the n, but we have another 1/2. That's going to be times 1 over 2 to the n plus 1. Any questions on the algebra there? I did a lot of algebra in that piece. Here's the harder question for you. Will you be able to do it?
With practice, hopefully.
Yeah, hopefully with practice. Again, you don't have to do it much for the assignment that's going to be due on, Friday, but you're going to have to do it later. So I figure I should tell you what's coming up. Okay. The whole point of this entire second half of the course is to be able to do this kind of thing, where you have a function of x, which is like x cubed over 2 plus x squared, and we can write it as a series. I don't know why you might even want to write it as a series, kind of practically, in terms of practical reasons.
Suppose you want to know how much stuff is in a domain of a function. Like, suppose you wanted to add it all up together. Or arrange, I would think, actually.
Right, but the point is, why is what I have highlighted better than what we started with? That's the question. Certainly doesn't feel better, does it?
Because that's an easier thing to sum up than what we had before.
No. What I have highlighted now isn't even a sum.
Exactly.
So that looks easier, doesn't it? But it's actually not. So let me tell you the reason. What we have on the far right is really a polynomial. Do you see that? Okay, it's just numbers times x to powers. And for example, integration is easy if you have polynomials. Do y'all agree? So is taking derivatives. Okay, and it turns out calculations are easier too. Polynomials are easy to deal with calculation-wise in terms of computers, for example, in terms of how long it takes to do the calculation. So what we're going to be doing in the last 3 weeks of class, maybe 2 weeks, is we're going to have functions, might be like this or even more weird, and we're going to turn them all into polynomials. So the whole point of what we're doing is to be able to do that. Okay, and this is just one example of doing it, where you start out with a rational expression and you end up with something that looks horrible until you think about it for a while. It's just a big long polynomial. And polynomials are the easiest things in the world to deal with when it comes to calculus. Do y'all agree? Okay, whereas if I asked you to find the 10th derivative of this sucker, x cubed over 2 plus x to the 4th, you'd frown a lot, wouldn't you? Do you want to use the quotient rule 10 times? Does that sound fun? Not at all. But if I said, what is the 10th derivative of this guy, it's actually not that big a deal because you're just taking the derivative of a polynomial 10 times. That's simple. Any questions on the kind of reason why we're doing all this? It's easier to get lost in the mess because this doesn't, when you look at this big summation sign, it doesn't feel better than what you started with. but it turns out it is for many, many reasons. Any questions on that? We will get back to it, by the way, in like a month. Not too bad? Okay, so we now understand how do you take a function and turn it into a series, okay? And we can figure that out. Now, let me give you another example. It's gonna look so much easier and so much not easier. Don't you hate those? I'm not gonna write example, I'm gonna write the example. Why am I gonna use the word the? Any guess? Okay. Yeah, it's only one, but it's not just important, but it rises so much higher above everything else that there is when it comes to series that diverge. It's the example. And let me just give it to you. It's very easy to write down. Let's look at it. I'm going to write it first in not summation notation, and then we'll do summation notation. Let's do 1 plus, very easy to look at. A half plus, I think I'm going to do a copy paste is easiest. A third plus, maybe copy paste is not easier. A fourth. What do you think comes next? Do you see the pattern? I hope you all do.
1/5.
1/5. Okay. It's the example, and it's called the harmonic series. And I'm just going to write plus, dot, dot, dot. First thing, let's write it in sigma notation. So it's the summation n equals 1 to infinity of 1 over n. Okay, this is a really important series. All right, well, you look at this. Do these numbers get, do the numbers get smaller and smaller? I mean, that should be obvious. If you go 1,000 out there, then what do you get? 1 over 1,000, right? So as you're going out and out and out, you're adding tinier and tinier numbers. Does this converge?
Yeah.
One more guess. So I'm going to shout it out spelling-wise. This diverges. Okay, it's the most important divergent series there is. And it's not obvious that it diverges. Okay, but it does, and I'm going to show you why. So this is more than just an example. That's why I put the word the in front of it. Okay, this is a major topic. We're going to be using it almost every day for the rest of the class for all kinds of interesting things. So this diverges. So now the question is, how do you know that? And the key is the following. I'm going to need more than these terms, but might as well start by copying those. The key is in grouping. So I'm going to go 1 plus a half I think I can leave it as a half, actually. Plus a third plus a fourth plus a fifth plus a sixth plus a seventh. I know it feels like I'm just wasting time, but trust me, this is needed. Plus an eighth. Plus. Okay. I don't think I'm going to write down the next group because we're just now talk about it. The one's not so important, but what we can do is the following. We can use a little inequality. So we have a 1 plus a half plus, actually I need a greater than. Now we look at a third plus a fourth. Do you all agree that a third and a fourth are at least as big as a fourth? Is that obvious to you?
Yes.
Okay, so a third plus a fourth is greater than 2/4. Do you agree? Because there's two of them that are at least as big as a fourth. What's 2/4?
Half.
A half. This is a beautiful proof, actually. I didn't come up with it, by the way. I think Gauss did, but I'm not sure. Okay, well, now we can look at a fifth plus a sixth plus a seventh plus an eighth. They're all at least as big as an eighth. Do you agree? There's 4 of them. So if you take something that's at least as big as an eighth plus an eighth plus an eighth plus an eighth, then it's at least as big as
Half.
a half. Is that clear? Okay, I didn't write the next one down, but the next one is going to be a 9th plus a 10th plus an 11th plus a 12th plus a 13th plus a 14th plus a 15th plus a 16th. There's 8 of them. They're all at least as big as a 16th. So that's at least as big as a half. Can I keep going forever?
Probably.
Is there ever a time I can't, take the next, doubled of them? Yeah, I can go forever and ever and ever. What do you get? What's 1 plus a half plus a half plus a half plus a half, et cetera, et cetera? That's infinity. So that tells us that our series is bigger than infinity. Well, if you're bigger than infinity, you're infinity. So it diverges. Any questions on that? Okay, so the harmonic series is a divergent series. Okay, and this is the proof. You don't have to prove it every time you do it, but you have to know that the harmonic series diverges. Got it? I want to give you the other important divergence series that I didn't talk about. And I want to ask you, what is the problem with this? There's going to be a problem, I promise. So if we have the summation from n equals 0 to infinity, of a, I'll even throw in some numbers. How about 3 times 2 to the n? Well, that's a harmonic series, right? So that is equal to 3 over 1 minus 2, which is equal to negative 3. What's the problem with that? Anyone see the issue? Hopefully you know that 3 plus 6 plus 12 plus 18 ... can't be negative 3. If you add them up, you don't get negative 3. You all agree?
Yeah,
What's
there's
the
no way.
issue? So what's the problem? Because I used the formula, right? Okay. I don't see y'all jumping in. The answer is the geometric series diverges for the absolute value of r greater than or equal to 1. So don't use the formula. For a divergence series. Okay, and that's just going to be true throughout the whole class. Is the first thing you have to do is say, does this converge? If the answer is no, it diverges, you're done. It diverges. Okay, you got to explain why it diverges, but don't try and find a number out of it. If the answer is converges, then sometimes you're interested in what does it converge to? And there's 2 ways of doing that. One is algebra, which I showed you, and the other is using a computer. Any questions at all on this kind of theorem, this answer about geometric series? And by the way, I should write it down, is if r in absolute values is less than 1, then the geometric series converges. Okay, and that's always true. Any questions on that? Any questions? Okay, we're about end of the day. So I'm going to stop my share and then stop the recording.